Thanks, Amy. I think the only reason the thing in Kuala Lumpur was popular because I think I was half drunk actually from the night before. We had been out on a crazy bender, but anyway, it was all good fun. I remember one in Amsterdam as well, which was similar. So, and thank you. This is a great intimate setting. Definitely different. If anyone's been to DEF CON, it's very different staring out at the audience from DEF CON. There's no one with pink hair. There's no one asleep, half drunk. It's very nice to be in a civil society for sure. So what we're going to do is talk basically about finding vulnerabilities in open source code, malware, other things at scale. And I'll kind of walk you through this flow. Dr. Sagi Sharma, who's based here in Singapore, runs our product R&D. So he's going to do 2 demos. But what I'm going to do is basically walk you through, first, help you understand why this open source thing is such a big problem, just the scale of the problem. And then we'll sort of level set around how open source actually gets used. A lot of people kind of, when you talk about it, are you talking about using Red Hat, etc.? So we'll kind of level set on that. And then we'll explain what can go wrong. And Asanka basically is going to come up and he will ransomware a web app. So basically, if you look at ransomware today, most people think it just operates on a desktop. It's going to be moving into online banking and online commerce apps. And Asanka will basically show you a backdoored library. We'll tee up how it will get put in, and we'll ransomware the thing. And if anyone is a developer here, when you go back to your desk, you should make sure that you do not run libraries like this, which you'll see. So after that, we'll just talk about kind of the standard landscape stuff, and then what we'll do is the crux of the talk, which is basically what we've built and what we're going to open source at the end of the year is a language to find vulnerabilities in open source code. So it's basically a language that sits on top of our graph structure, and we'll walk through that. And Asanka then will come up and we'll demo it live, and we'll run a whole bunch of queries and we'll find a whole bunch of things that are not been found before. So hopefully you'll see it, and then at the end you'll get to know how you can use it later in the year. So the first thing, and again, I'm just kind of teeing stuff up. Mark Andreessen has this famous phrase, software's eating the world. The reality is it's open source that's eating the world. If you look at all of the companies, Uber, Facebook, all of these companies that have grown up really fast, all the banks that have grown up really fast, it's open source that is powering that change. And it's to the point today where there's been a recent survey done, nearly 80% of the Fortune 500 say that open source is reliant, they're reliant on it for their business. If it didn't exist, their businesses basically wouldn't be able to operate anymore. So if you look at all of the online banking stuff that's happening, all of the analytics stuff that's happening, all of the life sciences stuff, it's all based on open source technologies underneath the hood. And that trend has got to the point where the US government now have mandated, and by the way, I'll make some Trump jokes about the US government, don't worry, we'll get there. The US government have mandated that 20% of all of the code produced by the US government has to be open sourced. So if they get something or build something, 20% of it has to be open sourced. And the NSA, for instance, have open sourced a thing called NiFi, which is basically a workflow routing system, which is used for routing intelligence. So these aren't like trivial little applications. The site for vote.gov was open sourced, which was how you registered for US voting. And it's also full of vulnerabilities, which I hope would explain why Donald Trump got in, but maybe not, I don't know. We'll figure that one out. So it's pretty significant. And of course, you recognize all of these names. Like none of these names would have been successful. They are open source core at their business. Google, Facebook, LinkedIn, Airbnb, all of these people produce massive amounts of open source. The reality is about the size of this thing is that what this chart shows is how many open source libraries are getting released. I'm probably going to fall backwards over here in a real comedy thing in a minute, but don't worry. So if you look back to 2011, there were about 160,000 libraries in total. So you can see the thing. Most people were building stuff in Ruby. Ruby on Rails was kind of popular. People were building commercial stuff in Java, and we were starting to see the rise of other things. The growth of this has got pretty substantial. So we're now at about 650,000 unique libraries. So that's libraries, not library versions. That's 650,000 libraries, and that's in those languages alone. So if you think about things like C and C++, which is mainly used in Linux stuff, Go, all of these other things, millions and millions of libraries. And then when we talk about versions, as you'll see in a second, we're talking about a significant amount of stuff. Certainly you can't keep track of it in a humanly or a spreadsheet. So that's the kind of growth. what we've also seen, if you think of it in terms of lines of code, we went from something which was kind of imaginable to something where we are today, which is unimaginable, right? It's like 1.4 billion lines of code out there in the open source world. So the romantic notion that open source, you can go look at it, of course you can. I don't know, there's some super smart people from my team down here, but like they can't look through 1.5 billion lines of code. It's not possible. And so if we also look at the other trend that's happened is if you wind back 5 years ago, the average library used to release about 4 times a year, just over 4 times a year. Today, the average library releases about 6 times a year. So what we've seen is this exponential growth in the numbers of libraries, and then the frequency in which they release has increased significantly as well. So one of our data science guys basically took that data and said, if the increase continues at the same rate we've seen for the last 4 years, and the trend of increasing in the number of releases increases, totally hypothetical, but we'll get to the point in 2026, so basically in about a decade's time, when we'll be approaching 500 million libraries. So the problem is getting pretty significant and pretty out of control. So to sort of set a context and really kind of just teeing up a Sankhya so you can kind of see how these things are going to manifest in the real world, the way people consume open source is basically like making a cocktail, right? So not a cocktail glass, I guess, but the first thing you do is you choose a framework. You choose a framework to use. So it might be Ruby on Rails, it might be some Java framework. And once you do that, you start writing your own custom code that goes on top of it. So if you choose Ruby on Rails, you'll be writing code in Ruby. If you choose Spring, you'll be writing stuff in Java. And you start writing that code, and then you start realizing that there are things that you want to do that you don't want to go build yourself, right? So I want to create credit cards. I go and figure out how I'm going to use Stripe, and I put in a Stripe library. I want to use logging, etc. And before you know it, basically what you've done is you've got a cocktail. And what that cocktail typically consists of at the end of the day is something like this, right? Where 90% of the code in your finished application was not written by you. So the Cisco guys that were on just now, when they build routers and they put a web-based interface on it, it's usually Apache struts, which was not built by them. So I've seen a slide that was photographed from some internal thing there that 75% of their code is not written by them. It's written by someone else. And so the implications of that from a security perspective are pretty significant, right? We've spent our time basically educating our own developers, spending our own time running static analysis and things through our own code, but 75% of the people, 75% of that code never got checked. We've got no idea where it came from. We've got no idea what it does, but it makes up that final piece of that application. And the way that this stuff gets distributed on the internet is we've got these today, 660,000 of these libraries. So we've got 660,000 of these lines. The developers or the teams working on that push it into their GitHub repo and work on that. And then when it's finalized, they'll push it into a distribution, centralized distribution system. So if they've got any Ruby developers, it's rubygems.org, npmjs.org, Maven Central, etc. So we've got this centralized distribution. But fundamentally, 2 things, right? There's where the code lives, and then there's where it gets distributed. And then what happens is when the developer wants to go consume it, he will basically specify what he wants to use. So he'll say, great, I want to use version, and between this range of this library, and in another part of the application, he says, I want to use this specific version of this library, and it gets run by a thing called a package manager. So in the Java world, it's Maven or Gradle, Ruby, Bundler, NPM, Yarn is the thing that's taken over, written by Facebook to do all the JavaScript dev. And what these package managers do is do a whole bunch of complexity on behalf of the developer. So they basically do all the heavy lifting, but they make loads and loads of decisions on behalf of the developer, and many of those are security decisions. They decide which version actually satisfies the criteria. So, for instance, I may say here I want to use between version 3 and 3.82, and locally I may have 3.7, which satisfies the conditions, and so it'll allow it to go. So it'll check what's locally on the build system, on the developer's machine. It'll go pull them from the central distribution system, and it will create essentially the final list of what's happening. And there's a huge amount of complexity that happens in there that can be abused. What happens from the developer's perspective is they basically choose, say, 3 libraries. But what actually happens then is those libraries then say, but I need this one to survive, and I need this one to survive, and I need that one. So it's kind of like 100 people can come into this room, but actually, or they go and invite all their friends, and their friends invite their friends, and before you know it, there's 700 people invited into the room. And the reality of why that's important is this is a log scale, you'll notice. So in the JavaScript world, the average application, the average developer says, I'm going to use 23 libraries, but when he actually builds the project, 430 get used. So imagine the scale of that this intimate little room here, I don't know, however many people's here, we could do the Donald Trump White House thing of, right, there's millions of people out there. Millions. We can take it in the photos, right? Millions of people, and then billions of people get used, right? But that's the reality of what happens. And the developer didn't choose these libraries, has no control over them, but they get used when his application comes in. In the Java world, it's about 1 in 4 app libraries to get used. Ruby world, about 1 in 6. But this JavaScript thing is really significant because this is the modern language and the modern way of doing things. And so if you go back to that vote.gov website that is now open, the code is open source on code.gov. They specified 19 libraries to be used. 600 got used in the final project. And of that, the developer only thought he was using 19. So it's a pretty significant problem. And of course, the bad guys know this, right? They know that the simplistic way of looking for these vulnerabilities is people consuming these things in their code. But the reality is you have to build the code, and that the smart guys are hiding these things deep into these dependency graphs. So with that, before we kind of tee up a sank here on the ransomware demo, there's a couple of really important trends. And these important trends are, as you'll see, why we think that ransomware is about to hit the hockey stick and is gonna start pushing up into server-side stuff. The first is that people are no longer using centralized distribution systems. So think of that centralized distribution system as basically being like the App Store, the Google Play Store, the Apple App Store. What's happening, and particularly with languages like Go, which is really taking off, supported by Google, is the developer pushes into his code repo, and then everyone who wants to consume just pulls it directly from there. There's no centralized system where it's going. So instead of having a couple of centralized distribution points, like a couple of app stores, everyone now is pulling from the individual ones. So imagine if you had an Android phone, and instead of pulling from the Google Play Store, all of a sudden you pull from every single person. Can you imagine the chaos, right? That's going to ensue. So that's trend number 1 that's happening. Trend number 2 is that we are now seeing all of the code being split into smaller and smaller chunks. And this is getting to the point where it's almost farcical. So it used to be the case you'd use a couple of libraries, those libraries would do lots of big things. Now what happens is people break those libraries down into really, really tiny pieces. So recently, last year, there was a library that almost took down the internet of everyone building in JavaScript. It was called LeftPad. It was quite literally 11 lines of code. And what it did is it padded something left. And that library, imagine it's one of these tiny little things, got embedded into the Express framework, which got embedded into pretty much every JavaScript, server-side JavaScript app that was being used. The guy had a Digital Millennium Copyright Takedown Act. He had another library called Kik, and there's an instant messenger called Kik. So he took it off the internet. All of a sudden, everyone's apps wouldn't compile, and everything broke. And it was basically because everyone was now using a function which would padded something 11 lines of code. So we're seeing massive modularity, and all of a sudden, everyone relies on something which is fundamentally deep down. And then the next trend, and this again, I'm kind of teeing up the ransomware thing, is that once we're now moving to this distribution model, so you can think of this as basically like BitTorrent, right? It's like basically that's what it is. It's BitTorrent for code libraries is what's happening out there. Instead of us having, Netflix where we go publish stuff down, we now just go pull it down from the individual places. And so now everyone is pulling from the code repo, and they pull the very latest bit of code that's pushed in there. So whatever that developer pushes in there, you get to consume. It may not be something that he's checked. It may not be something that's ready, but that's where you go pull it from. So with that context, massive amount of libraries, complete chaos, can't keep control of them humanly, lots of problems happening in how we consume these things. Someone, by the way, the Donald Trump kind of joke was someone said this is like fake news, right? It's like the minute someone says something, everyone else starts using it, but you always just refer to the last thing that someone said. I'm not sure if that's a great analogy, but I've got to get some Donald Trump jokes in somewhere. So if we think of these central distribution points as well, it's also worth thinking. So if you think about the Android Play Store or the Apple App Store, when you upload an app to it, there's a bunch of controls around it, right? First of all, you have to be verified, you have to be part of the developer program, you have to code sign it so you know where it came from. They have a bunch of technology at the back end to make sure that you are not distributing malware, you're not doing bad things. That's why apps take a long time to get published, right? They've put some controls back in that central place. But if we think about the current state of affairs with Java, so that's Maven Central, NPM.js, Ruby and Python, it's terrible. There are no controls whatsoever for consuming these libraries. So none of them check for any sort of malware, and there are instances happening now live. 2 weeks ago, someone published a library into NPM.js, and basically what it did is when the developer ran the build, it looked for the environment variables that were on the build node. Most developers put their SSH keys, their AWS keys, passwords on the environment variables. So basically what this library was doing was looking for the environment variables, and then it would send a copy of that back out to the equivalent of a command and control machine on the internet. And it took people a little while to figure out that someone had done it, and then they realized that that guy had 80 other libraries that were doing the same thing. And he hadn't hidden it. They were called like /hack or something, like was his username. Like he was blatant about it. But no one looked at it, and every time, everyone, either the person ran the build or the build server ran the build, all of those credentials would go. So none of these systems are doing that checking. None of them check for known vulnerabilities. They're all distributing libraries that are known to be vulnerable, and they will continue doing so. There is no mechanism to deprecate ones that have had vulnerabilities released in. You just carry on using it, and you have got no clue to figure out whether they're vulnerable. So it's kind of like, I would have to go track Microsoft to figure out what libraries I've got on my machine, which ones are vulnerable, which ones I should pull down. Not a single one of them do two-factor auth. So someone recently looked at one of these databases where people had exposed their usernames and passwords. They then correlated it with the emails that were up in NPM.js, and they claimed that they could have published 40% of those libraries in JavaScript because those accounts had been compromised. And we've seen cases where developers have also been basically paid upstream. They've built a following upstream. They have then sold their accounts because every time they can push that code down into something bad. And we've also seen some cases recently in San Francisco as an advertising company that is basically hijacking open source projects and injecting malware into them. So they basically take over the project, add some code, and then they influence it and put code in. You'd think that all of these things could be solved by code signing, so at least you know where things came from. Although in reality, code signing only solves one problem, which is once the letter bomb has gone off, I know who sent it. Like it doesn't solve any other problem. And that's not always that useful, right? Like once the bomb's gone off, it's kind of too late. I can find out where it happened, but it doesn't stop the bomb going off in the first place. So most of these have mechanisms to do self-signing, which is meaningless. It doesn't help at all. And Maven Central basically runs PGP, which is, I'm trying to make sure I don't swear, but it's kind of bullshit, right? It's like all it does is verifying an email address. And to prove why that's bullshit, I actually went and registered. I found one of the Apache lead developers on an Apache project. I registered a Gmail address. I registered a PGP key with it, and I pushed it to Maven Central, and it got downloaded 2,000 times in the first week. And everyone thought it was coming from Apache. Of course, it wasn't. All they were doing was verifying an email address, so it's not trust. So there is no real code signing in Maven at all, unless I magically happen to trust already one of the people that's already releasing that code. But it's very weak, to say the least. So Sankey is going to come up now, and what he'll do is show you a piece of malware, so of how this stuff is going to manifest into enterprise web apps. So basically, the kind of way this works is that the first thing you're going to do is we're going to publish a vulnerable library into one of these registries. He'll just run it locally because we don't want to do it, but we've done it several times. We've done it in NPM, we've done it in Java. It's not a language problem. They all allow you to do it, and there's loads of ways you could do it. You could just publish it under your own account. You could hijack someone else's. As you just saw, there's a million ways to do it. Once we've published it, anyone that is using that, so either we convince them to use a new library. In the NPM world, what we did is we found a very popular library, and we called it version 2. And everyone that was following that one suddenly started, of course, pulling down version 2, right? In the Java world, I basically took a similar thing with an Apache project and claimed it was that. So once we've got that, the developer basically just adds it in. He thinks he's using an innocent library. The next time he runs the build, that library will then get included, and then we just have to get the thing running. So with that, we'll flip over to a Sankya's machine if we can. Do you want me to shift that over?
All right, so we'll just jump right into the demo. So like Mark mentioned, there are two components. First is that we have a library which does something interesting. In this case, has a malware in it. So it's like aptly named here, ransomware. But it has some obvious functionality that you would want or you want to fool a developer into installing it. So it says like, okay, there's a class email validator and helps you do some validation, right? But inside this is valid email, there is a function which gets called, which is takeover Spring. So basically, this library will try to figure out whether it is running in the context of a web application, try to see the part of the code which is loaded in, so goes through all the classes, trying to figure out what database connections are there. So once you have access to the database, and you can use tricks like reflection, etc., you then connect to the database, you download all the data, delete the tables, and then you leave a ransom note. So what you can do, because it's running in a web application, you can just take all the views out and leave an HTML page with a ransom note, right? So you want people to know where to send you money. So this is the library. And then we're using it in a application which is just a starter kit for a Spring MVC app. And I just included this library, and it has a sign up thing, and I just call the is valid email. So let me just show you how it looks like. So it's just this. So you can just sign up. So let me just do that. Right, so it basically signs up. If you go down to the database, you can see that the account I created is there, right? So let me just log off and then see what happens if I try and sign up again. So this is when, because I'm already running the app and it already includes the library, this is when it would get triggered up. So when it tries to do email validation. So let me try again. You can take, like, it's taking a few seconds this time. And hopefully, right? So that's some ransom note. And if you want to confirm, you go back to the database, try to access it, and see it's not there. All right.
So if we could flip back to the other one. So all you had to do was get one developer to use one library that was malware, and it's over. So can you imagine that happening to Citibank? It'd be awesome, right? Like, instead of someone ransomwaring a 200, a small desktop, and you send me half a Bitcoin, it's like, how much are they going to pay when their entire database has basically been dipped and encrypted, right? It's like, and it's that easy. Anytime you use one library, no validation, super fast to go use. So we're already starting to see what the bad guys are figuring out, basically, is that reusable code means reusable vulnerabilities, and they can, in many places, get mass attack surface areas on these things with super high valuable targets. You can also go start attacking very specific things. So we're now living also in this world of GitHub, where if we wanted to go figure out who's following Spring or who's using Spring, you go to GitHub, you watch the watches, you see the companies they work for. So we're seeing that as well. We're seeing people socially target these apps. So what are we doing for time? 21 minutes. All right. So that's how easy it is for bad stuff to happen, and we think that stuff is going to happen on a regular basis. So this isn't just about vulnerabilities, right? This is about vulnerabilities. It's going to be about malware. It's going to be about libraries doing bad things, and it's going to be pervasive across developer stuff. The first thing is the kind of like the current state of generation for people finding these vulnerabilities, or the first generation of this, it's just kind of still what a lot of people do, some of the open source tools do this, is basically what they're doing is basically mapping CVEs, common vulnerabilities and exposures, to library names. So it's basically grep, essentially, is what it is. You look at the library name, you figure out what the library name is, you match it to a vulnerability, and you map it back. Pretty useless. The majority of the libraries sit underneath that pit. They're not specified in the code. So very easy to go bypass that, and the same with licensing checks and other things. The current state of the art for this is basically sort of the next generation of that, which is you look at the entire dependency graph, so you figure out exactly what is getting built, And then you run a trace down to figure out, are you actually using the vulnerable part of the vulnerable library? It turns out that just because you include a vulnerable library, 90% of the time it never gets called. So if you want to figure out whether it's exploitable, you have to actually know whether you're using the vulnerable method of the vulnerable library, of how that works. And it also turns out that the vast majority of the vulnerabilities don't exist in the CVE ecosystem. So CVE, as I'm sure everyone kind of knows, has been this de facto database. I think someone spoke about it, the Talos guy spoke about it this morning around a bunch of CVEs. But the vast majority of security issues in open source code don't exist in the CVE ecosystem, nor will they ever. If you imagine it's basically run by a US government contractor, they take weeks to respond to everything. And here we are now living in a world where developers, these hipster developers, like if anyone's been to San Francisco, they ride around on these little fixed wheel bikes, like plaid shirts, big long beards. Like they're not going to report a vulnerability to a government database. It's just not in the ecosystem, right? It's like the difference between your parents' music and kids' music. Like there's just a fundamental difference in the way people are building stuff compared to that ecosystem. So the current state of the art, which we're doing, and so folks, is basically you have to look through these public advisories, the CVE things, and the first thing you have to do is a set of secondary analysis to figure out whether the issue is actually real. It turns out that a lot of the CVEs are actually incorrect. People will publish and say, this library has this issue, but actually it may turn out that it's a library that is using that library that has that issue. Or it may turn out that it's actually a completely different library. So the CVE stuff, first of all, it's written in a piece of human text, which doesn't allow you to describe what the actual problem is, which is part of the problem we're solving with SGL. It's contextual. It's a human description of something. And secondly, in many cases, it's fundamentally wrong. But the next thing you have to do is also start looking at where these people are hiding these issues. And it turns out that what you can do is you can look at the commit logs of where the developers were first pushing that problem in, and you can see where they're fixing the problems in the first place. So we've been spending a lot of time running both data analytics and experimenting with some machine learning to parse those commit logs at scale, and it turns out it's an incredibly rich source to find out basically where they are finding fixing issues that they either just can't be bothered to tell anyone, or finding fixing issues and just simply putting the information in there but don't go up and get a CV. And these things turn out to be essentially private vulnerabilities. And this is a little bit hand-wavy, but we were trying to figure out, of the total size of the vulnerability pool, what would it be if we scaled up that system from looking at those upstream commit logs to all of the vulnerability, all of the library population that sits there today. So there are a couple of thousand CVEs in all of those library systems. I think it's like 1,943 or something. Asanke will go through it in detail, of those 4 languages today. But if we continued scaling up the machine learning, looking at the commit logs and parsing the commit logs of all of those libraries, we would probably get to a vulnerability pool of just over 250,000. It'll be somewhere between where it is today and 250,000. And it's hard to know for sure because there's, of course, a bias. The ones that we're starting to look through now have likely got a higher vulnerability density than some of the less used libraries, and there's a lot of things. But it's certainly not a couple of thousand issues, and it's a very large number that is sat there, that is currently unreported and currently undetected. And of those, the way to think about them is this kind of taxonomy. There is a set of vulnerabilities that get inherited, and Asanke will show you an example of this. So what he'll do is he'll show you all of the libraries that are vulnerable because they inherit the Apache Commons serialization problem that no one could surface before. So in this SGL language, we can surface it. So one library at the top gets used, another library then uses another library, and they wind up consuming it and basically inheriting the problem. So it's kind of like Dylan invites me here, I invite Asanke, and Asanke invites his cousin who is going to trash the joint, right? It's like that's kind of like the way it works. We just don't know how it works. Asanke does not have a cousin who trashes the joint, by the way. Very upstanding family, just to be clear. Obviously, the disclosed issues, there are a set of similar issues. You can extract patterns out of these. So we've looked at some of these vulnerabilities and we've said, hold on, like that's just a common problem. Where else does that same problem occur? So pretty recently, there were about 300 CVEs that came in of basically Android apps that weren't validating SSL certs. Well, guess what? When you sweep across the rest of the ecosystem, there's loads of apps that don't do the same thing. So you can start looking at those. You can also start looking at things that get embedded. So whether developers start cutting and pasting vulnerable code and putting it into different places, or whether people start embedding one library inside of another, either innocently or in some cases maliciously. They're trying to hide it. So in this first generation of these tools, they were basically just looking for a library name. Well, guess what? If that library name matches something else, but inside of it is the malicious package, you can just go and hide behind it. We've also caught cases where people were reintroducing things. So in the development workflow, you have branches of code. So the Spring framework, one of the biggest frameworks used to power loads of online banks, all sorts of things, they fixed a vulnerability in one branch, didn't fix it in another branch, merged that branch back into the master branch, and then reintroduced the vulnerability that they thought they had fixed. And it just so happened anyone could then log in using social login to an online banking site, basically. Like, pretty significant problem. What we're calling half days are these vulnerabilities that are not disclosed, but if you know where to go look, you know where they are. They're buried in commit logs, buried in issue tracking systems, etc. And there's a whole set of these things. And so this next generation of finding these vulnerabilities is basically going to be focused on behaviors, rules, and patterns. So think of the change that is happening is it's like the antivirus industry 15, 20 years ago, whenever it was, when every single virus that would come out, someone would go write a signature for. That's kind of where we are today. But what we're now is moving into the place like we did with virus stuff, where it's basically about heuristics and patterns, because you can't keep up with the number and the variance of these things. And that's the fundamental shift that's happening today. The difference in an open source world, though, is that we're living with this big ecosystem of all of these vulnerabilities. So it's really akin to gene engineering, figuring out all the sequences and all of the patterns of the genes, and figuring out how they're interconnected, and figuring out how to build the relationships. And then given the size of the data that we're dealing with, we have to be applying good computer science to this. It can't be done by hand. Certainly some tools that can help. And all of these things are highly likely to come out in private vulnerability databases, not the CVE ecosystem. They can't cope with the volume. You know, we know about thousands of things. Like, we can't just mint thousands of things. The CVE stuff gets unverified. So they are likely to start surfacing in these private vulnerability databases. So Asanka will come up, and so basically what we've done, so we're going to open source the specification for the language probably towards the end of the year. We've got it running in Java right now. We'll be adding all the other languages, including C, C++, Go, etc., before the end of the year. And then we'll publish a reference implementation of it as well. So a reference architecture. It's a big data system, so it's not like you can just go download the thing and install it on your laptop and go play, as you'll see by the size of it in a sec. But the goals of the language were basically to allow you to ask sophisticated questions around the open source. What uses what? What inherits what? Where do methods get traced across what? Where is the same piece of code across all of the ecosystem? And then allow you to go share that finding in a way that is repeatable, executable, and provable. Essentially a test case that you can give to someone else. So instead of someone saying, great, here is a CVE, and here's what the word describes. This may have a denial of service condition in this library under certain conditions. And if you ever want to go find things, there are some absolute howlers of CVEs that just describe the most generic, random things ever. But the goal is to have something which is executable. You can look through it, you know exactly what the problem is, and you can share it with someone else. You can give it to a different system, it becomes an executable test case that you can go prove. So if you want to give it to a developer, here's what the problem is. You're using this part of this, and this is what it does, and here's how you can prove it out. And then allow the research community to go and extend them. So like, here's a pattern. Oh, look, here's another pattern. I want to try and extend that pattern and go find more vulnerabilities. And so the basis of the system is this. What we've basically done is built a global dependency graph and a global call graph. And so for any developers, that's no mean feat. My wife goes, yeah, so what? But it's pretty cool. And it's built on a graph database which underlies this. And we're actually using the same graph database technology that Netflix used to power Netflix. So you can imagine the scale of this thing. It's DataStax Enterprise. It's built on, DataStax Enterprise is built on Cassandra. Cassandra was the big database that came out of Facebook. So it is very large. And what we basically do is we take that world's open source code, all of those libraries, and we generate a set of abstractions off of that. So we build a global dependency graph. So we figure out for every library, what does it also need when it gets built, and what are the relationships between that. So you build that for one, then you build it for another, and you realize that that one actually requires this one, and then you go, oh, great, so then that one requires this one, which requires this one, which requires this one. And you build up all of the relationships between all of those millions of libraries. And for every single version, not just the top-level library, for every version, so you can see the changes between it, you can navigate all of the combinations. We then also build a call graph for every library. What happens, what does it call, how does it work? We build an AST, so basically an abstract syntax tree that describes the code. We can also do things like binary similarity. So show me, like this jar file is actually the same as that one, even though it claims to be slightly different. Or this one is 90% the same as that one. So you can do a whole bunch of things like that. And then what you do is you also codify the vulnerabilities. So you figure out like where are the vulnerable methods, where are the patterns, and all of the different things. And it goes into this giant, great big graph database. That graph database then can be queried with a thing called Gremlin, which is a graph query language. And then on top of that, we've built this security graph language. So the security graph language basically compiles down into Gremlin queries, and the Gremlin queries then run across the database. Underneath this large graph database, you can do OLAP and OLTP and all of the normal processing things. And that allows you to do is to basically spawn an interactive shell and ask a set of queries about that world's open source code looking for vulnerabilities. Or you can write a programmatic program that looks for it and will just run constantly. So what this will allow us to do is that the minute a piece of code is published upstream, you can then run a barrage of checks against it before the thing will ever get consumed. And that guy that was producing that thing, that was looking for the environment variable, would have got flagged before it could have got consumed. So you can start cleaning the upstream pipes of how this stuff's going to happen, but also look for the issues at scale. So Sankey will come up now and we'll demo it. But to give you an idea of the scale, someone built this beautiful diagram of Node. So this is actually a representation, a graph representation of 35,000 libraries. And all he did was basically look at the first depth of those libraries. So it was libraries and then which was the first one that it was relying on. So as you can see, it's pretty complex. But that was built with 35,000 library nodes. So far, in Java, we have about 340 million in our graph database, in the Java library alone. So there's no way we're going to waste time visualizing it at this point. Like, I don't know what's going to process it, but it's certainly pretty big. And then imagine that by the time we get all the languages in there, this is genuinely kind of big stuff. So what happens then underneath that hood is in that call graph is that imagine a piece of code. We know the library version. We know the call graph of the version. The vulnerability may say, great, here's where the vulnerable method is. We can then traverse down the complete graph to trace exactly where that problem is. And so Sankey will come up and explain the syntax and then basically open a shell, and we'll go run through a bunch of specific queries finding some issues, of which I think a couple of them for sure are definitely not released public, right?
Yeah, thanks. So this is just to show the syntax is actually pretty comprehensive. I'm not going to bore you with all the details on it, but best way to look at it is to go through some examples, which is what we'll do. So we have 6 different examples to go through, and hopefully they will give you a flavor of how you interact and work with this language. And what I'll do is, instead of showing you the final query that runs and finds a particular issue, I'll walk you through it. So this is how like a typical session for a security researcher or an engineer working with this system would look like. You start at some place, you explore a little more, and then you go on. So we are going to look at 6 things. One is, first we'll look at all instances of an embedded vulnerability. So this means, so we are doing it in Java world, so we'll look at a particular vulnerability. We'll see all the libraries which are affected by it. And then we'll look at all the other libraries which are affected by the same issue because they copy the class files or they copy the jars which are affected. So this is what Mark mentioned is bytecode or binary similarity. So this is not based on a package manager. So they don't mention it as a dependency. They literally copy the code or the class files. Second thing we'll look at is instances of inherited vulnerability, which is a library uses a dependency which has a known vulnerability and calls a vulnerable method inside that library. So that's what we call inherited. Then we'll get some queries which show some numbers, which is like an impact of a disclosed vulnerability, where impact is So if you come in and say, hey, this particular version of a library is vulnerable, what are all the other libraries in the entire Java ecosystem that depend on that version? So you can take a look at that and see a real impact of a particular vulnerability.
And the reason why that's important is when Heartbeat first came out, it was basically a low-risk vulnerability. No one realized quite how much it was impacted. But now what you can do for the first time with like the Apache Commons serialization is you can actually realize all of the other things that are actually using that, therefore what the impact is going to be.
And then we look at some hotspots of dangerous coding. So you can use it to query arbitrary things on the call graph and dependency graph. So it doesn't really have to be a vulnerability. You can just look for a pattern that you know is likely to lead to some security issue. So you can look for it, or you can look for interesting things like all libraries that have a main method, or all libraries that do runtime.exec. So we'll take a few examples and we'll see how many libraries do these kind of things. Then we look at a particular pattern, which is for a similar vulnerability, and I think we are going to do XXE. So we'll take a look at how easy it is to go from a pattern that you would describe in, say, Java code into SGL, and then look for the occurrences of those patterns. And the last one, which is my favorite query, is where we'll end with kind of like the state of the entire Java ecosystem's security. So we'll have a single query, 6 clauses, and it will give you all libraries across the entire Java ecosystem that are affected by all the known vulnerabilities. And we'll take a look at that number in a minute. So what I'll do is I'll walk you through the examples first, and then I'll go back and run them in the shell, just so that you have a flavor of the syntax which comes in. So like Mark mentioned, so we have a vulnerability node. So the way we query a vulnerability node is, if I can find my pointer. So it's something like this. So this vulnerability has an identity 1847. In this particular case, it's the Apache Commons Collections deserialization vulnerability, which happened last year. And when we add has version range, we can actually see all the version ranges of the libraries that are affected by this vulnerability. So let me just do this one first, maybe. So here's I'm on an interactive shell, right? And I see that these 7 libraries are affected by this vulnerability. And what are the version ranges which are affected? We can see right here. So this is from 2.4 RC1 to 3.0 beta, etc. Right? So this is more typical of like a signature for a particular vulnerability, which is what we have in the system. So from here, we can actually go back up and see all the instances of libraries that are affected. Right? So what we saw now was just the version ranges. So if you want to see the instances, you can do has library, and it will show you all the individual instances which are affected. So in this case, there are 61 library versions which are affected, right? And then, so remember we are doing the first query where we wanted to find out all the other libraries which copy these jars into them directly. So this is based on bytecode similarity. So what you do is you do just, and we call this embedded, right? So this tells you there are 11 libraries or which actually copy one of these vulnerable libraries, right? So this is actually showing you 11 libraries which copy the class files or the jars directly of a particular vulnerable library, in this case, the Apache Commons collection, right? What you can do is in all of these queries, you can actually add a star. So it would compute, so because remember this is happening on a graph. So without the star, it only looks at the direct edges. So if you add a star, it does a full transitive closure. So it will look for all the direct and indirect edges. In this particular case, there will be no difference because once you copy it in, it's in. But I'll show you an example where there will be a difference. Here's the second one. Right. So we start again where we were. This is has library, which is all the libraries which are affected by this particular vulnerability. And then we look at all the dependencies of these libraries, right? So like 843 libraries which depend on one of those 61 libraries that were affected by the vulnerability, right? And now, if you want to see the entire thing, which is all the direct and indirect ones, you just add a star. I think this will take a few seconds to return. But once it comes back, you'll see there are actually 10,000 plus libraries which are directly or indirectly affected by this vulnerability. Right, there you go. And now if you wanted to combine the two, so you want to figure out all the libraries which are either copied in or are actually directly or indirectly affected through the dependency graph. So you can do this, and this will give you a true impact of a vulnerability, right? So this is live. So we have all versions of all Java libraries in the system. We have a particular vulnerability, which is in this case Apache Commons Collection deserialization, and we are looking at all the other libraries inside this graph which are affected by this, either directly or indirectly, or because they are copied over. So that's a single query that gives you a true impact of a particular vulnerability. So imagine doing this when you have a new vulnerability. So when we usually try to score vulnerabilities, we use something like CVSS, where we assess the risk of a vulnerability. We can actually use something like this to find the true impact the vulnerability would have on the open source ecosystem.
And the great problem when that vulnerability was first released last year, everyone started panicking and no one knew where it was being used. But now, with this system, you can immediately know where else it's going to be used, and we'll figure out where else to go fix it. And as you can see, there's quite a scale to go do it, right?
Right. So if you're wondering, so what? So I could find all the libraries that actually use a particular vulnerable library, but it doesn't really mean that it can be exploited through that library, right? So you may not be calling that parts of the library that are vulnerable. So in this particular case, if you're not doing any deserialization, it doesn't matter, right? Because this was a vulnerability in deserialization. So for that, what we have is something we call vulnerable methods. So each vulnerability is annotated with vulnerable methods. And in this case, these deserialization methods are the vulnerable methods. So what we can do is we can go from the dependency graph onto the call graph and look for all the libraries which call this vulnerable method, right? And well, I can do that this way, as vulnerable method called by. So this will give me a list of all the methods that call these vulnerable methods, right? Now I can figure out what libraries these methods are in. So I just do method in library, right? So I think this will take a few seconds. I will return all the libraries which call where these methods are called, right? So these are all the potential libraries which call this method, which is one of the vulnerable methods, right? But they return all possible versions. So we don't really want all versions. We only want those versions which depend on the vulnerable Apache Commons collection, right? So the way to add that in is you go back up into the dependency graph and you can use a where clause. So let me just backtrack here. Right? So I add a where clause where I say the libraries out of these 6033 have to be in a version range where the version range has to be in a vulnerability, and that vulnerability is actually the same vulnerability that we are dealing with. This is the Apache Commons collection. So when we do this, this will only return those libraries which are directly dependent on that vulnerable library, and they make a call to the vulnerable method, right? And
so
then
if someone wants to go poke around and report 23 CVEs. There's 23 there. Apache directory services. Anyone use that? Want serialization? There's probably some interesting things to find. Right?
And if you want to go back up, like I said, you want to find all the dependencies and the things which are copied over, you just add embeds and depends on. So this is embed star right here, and then depend star. So this will give you the full list. And I think there are like 58 items if I'm not wrong. Oh, like there are more. Yeah, 184 items, right? So now these are all the libraries which inherit this particular vulnerability. So next are some very easy queries we can go through very quickly, which is finding certain interesting method calls. So this is looking at all the libraries which call, say, runtime exec. So
if you haven't thought about why that query is right. This is a Java library that is basically running exec after it gets run, right? Should never happen in a web app. It's often a sign of malware, someone's spawning a shell, basically, right? There may be cases where that might be useful, but should be pretty unusual.
Yeah, so you see like there are actually 10,773 libraries which do runtime exec. If you want to see libraries which are forcefully calling the garbage collector, so you can check this, and I think 2,000 plus libraries.
So you see this in like signs of malware where people are basically trying to clean up the memory after they've done something, right, inside of the behavior.
Or you just want to see all the libraries which connect to a database. So this list is really huge, so I'm going to limit it to 100, but you can see, I think this was...
So that example Asanki showed of that ransomware, he was basically using that library to connect and sniff the database connection, which is behavior which you wouldn't normally expect to see.
So you basically can combine these three queries to actually detect some library which I just demoed in the first part of the talk. So you open a connection to database, you try to run some commands, you use reflection. So use a combination of these patterns, and then you can look for things like malware. So it's like a bunch of libraries which do that. Then so this is an example of how you can use it to not only look for known vulnerabilities, but look for patterns of bugs or defects. So if you've used like XML parsers in Java, if you're not careful, you may run into like XXE attacks. So one of the things you do to prevent this is you may set feature and disable, external entities. So this is how this piece of code would look like, right? And it's almost very easy to convert it into a query which will look for an absence of this kind of behavior. So here what I have is a method which is new instance, and then another method which is called set feature. And what I'm doing is I'm trying to look for all the libraries which have a call to a new instance but do not make a call to the set feature method, right? So there are potentially cases where it might be vulnerable to a XXE. So let's take a look at that and see how many libraries we get. So here it is. It'll take a few seconds.
So we checked online last night, there were 43 CVEs about open source libraries that exhibit that behavior that have been reported.
So this is actually library instances. So you see like 12,589 instances. So we looked at, because it includes all versions, so we looked at the unique libraries in this list, and I think there were around 503 potential libraries which match this particular pattern.
So each one of those needs to be looked at. That behavior, it's possible that it's doing that check somewhere else in the code. So who knows? But even if it's 50%, there's 250 XSEs against the 43 that have currently been reported by the CVE ecosystem. Right. And you can pop them out instantly, right?
And now time for the final query, and I'll start running this because it might take like a minute to finish. So what you see, what we're doing here is we're looking for, so we use a wildcard. So that means we go through all the vulnerabilities. So these are all known vulnerabilities in Java libraries. We try to find out what libraries they affect. So this is has version range, has libraries, so individual instances. And then we see all of the ones which are directly, indirectly, or copied over. So you take all libraries that are known in Java, and you look for all possible places they are copied over. And then what you get is, and I think it will finish in a while, but what you'll see is there are more than 6,548 unique libraries which are affected by existing known vulnerabilities. Right?
So that query is traversing all 340 million nodes, and it's going through every single method call of every single node and figuring out where a vulnerability is being called, inherited, or any of those instances. And it'll take a little while because it's traversing every single possible thing. But what Asanki showed on the other thing is the stats. There are, of CVEs, of those Java ecosystems, there are today nearly 2,000 known vulnerable libraries. But actually through this, we know that there are actually over 6,000 vulnerable libraries. There are 3 times more in the current known stuff today, even before looking at all of that other stuff. So if you're interested in finding out, there you go.
So let's finish it. So there are like 68,341 versions, and then we looked into it, and we found there are more than 6,500 plus unique libraries.
So I'm just conscious of the time. So we'll, I don't know if you can flick back to my my thing. So that's SGL. So SGL will be open source. The language specification will be open sourced at the end of the year. we are going to open up a researcher program, and that researcher program will be for invited researchers that can basically use the infrastructure. It's a massive infrastructure, as you can imagine, to get all of that stuff going, so no one can get it up and running. The hosting costs are, of course, obscene and everything, but you will be able to come in, you'll be able to write SGL queries, go find vulnerabilities, and go expose them back out. So hopefully that'll be of interest to people. Go to sgl.org, and that's where you can go sign up for that. I think we're 10 minutes over, so I was normally asked for questions, but we probably shouldn't ask for questions at 10 minutes over, or even more than happy to take them if
there's a quick hand for a question, anyone raising a quick hand, then we'll take one question. They'll have the questions
No
off
quick
the
hands,
stage.
no heckling. All right, good.
All right, thank you
very
much.